Good evening, everyone. Welcome all of you for the week 10 live session of Smart Grid Basic to Advanced Technologies NPTEL course. And this is after this, we'll be having only 2 more weeks to follow, and then we will wind up this course, these live sessions for the course. I am Gagan Meena. I am a fourth year PhD student at Electrical Engineering Department of IIT Bombay from power system and power electronics specialization. Let us begin with today's live session now. This will be the agenda for the today's live session, and this is the same which we have been following in the previous weeks as well. First of all, we will go through the overview of week 10 and then we will discuss some questions. In between, we can also take up some topics related to the questions and uh, discuss them in further details. And then in between and after the session, you can ask the doubts. As a simple reminder for all of you, the deadline for assignment 11th is March 2nd, and the deadline for assignment 12th will be March 9th. And I hope all of you are able to access these recordings for the live sessions. You can find them in the problem solving sessions tab on the portal. There you will find the Google Drive link where you will find the links for all the recordings of the live session, as well as the link for the Google Drive where you can find the material used for all the 3 TAs for this course. And just after this session, this live session ends, I will upload this PDF for today's live session also on the in that same Google Drive. You can access it. Okay, so we'll begin with the week 10 overview. In week 10, we already discussed that starting from the previous week, that was the week 9. In week 9, the demonstration started, right? Last 4 weeks from week 9 onwards, week 9 to week 12. All these weeks are based on demonstrations. Here will not be talking much about theory, although that will again be revised in many times, but the content is more focused towards, more geared towards showcasing how we can implement what we have theoretically understood, the different control techniques, the control algorithms, or the mechanisms which we have studied, the architectures which we have studied. How we can actually use them in simulation first, and then finally go to the field. Because whatever concepts that we have studied from week 1 to week 8, that was theoretical aspect. And before applying them directly into the field, we want to create a AC microgrid, let's say, and we cannot directly go and connect our AC microgrid to the existing grid or DC microgrid or hybrid AC DC microgrid. We cannot directly do that. Let's say we want to connect a new generator to the existing transmission system, a new thermal power plant or nuclear power plant, or even wind or solar power plant. Or nowadays we have storage also, energy storage, lithium-ion batteries, or pumped hydro storage. Before interconnection, because it's a huge system, and We're not talking about a small at these voltage levels which we have at our homes, 240 volts. We're not talking about that. We're talking about kilovolts, and these power levels are very high here. And a small mistake can create a lot of problems to the existing system, which is a very costly affair, and it can also disrupt the power supply to the consumers. Before integrating any kind of new equipment, or let's say new generation or new transmission system to the existing system, we need to conduct thorough detailed studies. And one of the aspects of that is simulation. But till week 8, we have studied different theoretical aspects regarding distributed energy resources, concepts of microgrid, cybersecurity, how to integrate microgrid, what are the different modes of operation of microgrid, grid connected, islanded, and then transition from grid connected to islanded and vice versa. All these things we have studied, and we have studied different types of architectures, centralized, decentralized, distributed. All these things was required to do any kind of simulation. And then finally, once we verify what we have studied via simulations, then we actually go for a small test bed, or we can or directly go to the practical system and integrate it. But first step is the simulation, very detailed simulation where each and every component is modeled in its detailed fashion. So all these week 9 to week 12 sessions, the content is based on demonstration, based on simulation and small hardware setups where we are going, where we can verify what we have studied. That is very important. Okay, so here in this week 10, the demonstration or the simulation, initially these first three topics were based on simulation of AC, all the three kinds of microgrid, AC, DC microgrid, and AC, DC hybrid microgrid. And then there were demonstration. This was a small hardware demonstration of parallel operation of inverters in AC microgrid, and last was a theoretical. Last was it was not a demonstration. It was a topic, again a theoretical topic based on harmonic effects and its and different mitigation techniques for those harmonic effects. Okay, so we'll start with this simulation and case study of AC microgrid. Here we want to do a continuous. We want to mimic the actual system. We want to create a simulation such that it mimics the actual system. There are different types of simulators available. This MATLAB is also a kind of a simulation platform. We have PSCAD. Different softwares are there. These are offline softwares. These are not online. Say once we develop a model in Simulink, so in MATLAB we have Simulink, which is its simulation platform. In Simulink, we develop a model, any kind of, let's say we are talking here about AC microgrid, so we develop a AC microgrid model in Simulink, inside Simulink, and then we run it. It will take some time. And if we change something, then again we need to run it and again. So we keep we have to again and again change parameters and see, and that will take some time. It is also it is slow, and it depends on the system on which we are running the MATLAB, its speed of operation. The computation time, the time taken by the model to run will depend upon the system on which the MATLAB is installed. Similarly, same is the case with PSCAD also. These are offline softwares, and we cannot integrate. These are simple softwares. They don't have any hardware associated with them, and they will work on the system on which they are installed. But there are certain softwares which and there are certain hardwares which have their own software also, and together they can do computation in real time because there's time steps. Let's say here in MATLAB also we can specify time step in Simulink. At what time step we want to run the model. As you would have seen, there is one option when we go to configuration parameters in Simulink, you will find option for time step, and we can also specify the solver, different types of solvers for ordinary differential equations. Let's say the time step we have set is 10 microseconds. This is a time step. So the model will be solved at each 10 microseconds. Although the model will be solved for each 10 microseconds, but the time required to solve the model for each of these 10 microseconds, and let's say we want to simulate the model for 1 second. For each 10 microseconds, within this 1 second, the model will run in Simulink, and it will be very slow, very slow. If the model is very large and the time step is small, then the model takes a lot of time. This will happen in the offline this simulation platforms. But in online simulation platforms, for example, this OpenRT and so online, we have online simulators like real-time digital simulator, RTDS. We have OpenRT. We have Hyperloop. These are more used for power electronics. And this RTD is specially designed for power system. So this OpenRT is generally used for control purpose, control of these power electronic devices. Similarly, Hyperloop also. And these are the hardware platforms, and they have their own softwares also. Or in OpenRT, we can integrate the OpenRT, we can use the hardware in the OpenRT, but the software we can use Simulink. Same MATLAB can be used to run. Instead of running the MATLAB on our system, we can run the same on OpenRT. OpenRT will integrate with the MATLAB. So here I told you that if we run the model for each 10 microsecond, the output we will get after maybe 10 minutes, 15 minutes. It will take so much time. But in RTDS, if the time step is 10 microsecond, so it will solve that within 10 microseconds itself. So it will not take much time. It will do that within 10 microseconds. So it is as if the system is running online, as if the system is running in real time. As if we are solving the system in real time. Everything is happening continuously on a continuous basis and very fast because of the processors used here. So these are very high performance processors, RISC-based processors, FPGA-based processors used in RTDS, and which enable us to do real-time simulations. and that we are going to see here. So the advantage of this real-time simulation, these hardwares help us to perform real-time simulations. Real-time simulations. And the advantage of real-time simulation are we can do continuous real-time simulation, and we can also do hardware in loop testing. All these hardwares can be integrated with the device which you want to test. We can create a small test bed. You can have power amplifiers and whatnot. Whatever we want to test, we can create a small microgrid in the lab itself and integrate it with the RTDS. The entire control strategy, entire grid, we can emulate. We can make the transmission system within the RTDS, or we can make the control. The control system we can make within the RTDS, and we can have the actual hardware outside. We can have, say, we will see in the next slide. Here, the real-time digital simulators or OpenRT, RTDS, they help us to do continuous real-time simulation as well as hardware in loop testing. So before actual delivery, before the physical interconnection of the microgrid, we want to do such kind of analysis. And these continuous real-time simulation are very fast as compared to the offline programs similar to the Simulink in MATLAB. And these simulators operate in real time as if they are mimicking the real microgrid system. And they respond in real time to modification in parameters. If you change something, then they will act as if in it is happening in the real system. Let's say in the real system outside, if we have actual microgrid and it is connected to the grid and there is a fault, then whatever changes happen and the time which it takes, this real-time digital simulator will also mimic the same thing within the same time period. So if we create a fault in RTDS, then it will also take similar time. And the similar behavior will be seen here also. And the time taken, everything will be similar to the real system. That's why these are real time, they're called as real time simulator. They're very, very fast. And their time step is in the order of microseconds. So they can simulate the real world phenomena to very high accuracy and provide result very fast, very quickly. So that is one advantage, very important. And second is hardware in loop testing. Let's say we want to, because before the actual realization of the AC microgrid, we want to create a small test bed. So in the lab, we can create a small AC microgrid. We can have all the components. We can have a small PV emulator. We can have a small wind emulator. We can have a diesel generator, small diesel generator in the lab. We can have a small battery, lithium-ion battery, boost supercapacitor, fuel cell. Everything we can have within the laboratory, and we can have this entire control strategy we can implement in the RTDS or OpenRT, whichever platform we want to use. And then we can integrate, we can connect. Let's say this is the grid, and this we can create in lab using a grid emulator. This grid emulator will act as if it is a grid. It will act as an infinite bus, providing one angle zero. And then we have a AC microgrid here. And here we have different types of loads. We can have small loads in actual physical loads. Then we can have here diesel generator. We can have PV, wind, then small battery. And we can also have this small transmission line in the lab. Everything we can have, and whatever control strategy is there for these equipments, or you can say the microgrid control center. Control logic we can implement in RTDS. And we can take output from RTDS and give this control signal to each of these elements. And from, because we want to control them, we need input. We need their output, the output voltage of PV current. So this RTDS will take inputs from all of these. Input from PV, wind, battery, supercapacitor, fuel cell, and it will give control signal to each of these control signal. And now because these control signal are always limited to 5 volts, whatever control signal output we get from the RTDS, it will be in the range of 0 to 5 volt. But the actual okay, we can give the control signal here. But the input which we are receiving, we are getting, inserting into the RTDS, this will also be in the range of 0 to 5 volts. But the actual input, the actual voltage of PV, actual current will be much more. It can be 230 volts. We need to convert this 230 volts to 0 to 5 volts. For this, we require power amplifier. In between, we have a power amplifier which does this job. It can convert 5 volts to 230 volts, 230 volts to 5 volts. So in hardware, in loop testing, we require this power amplifier. We will have RTDS and actual small these hardwares for each of these elements. So we can create a small prototype of the actual microgrid, AC microgrid, or any system. You can have a small prototype of that in the lab, and we can see the behavior, how the simulation was working, and how the small prototype is replicating that simulation. And once uh, we are able to validate everything, then we can actually create a big scale, a large scale actual AC or DC microgrid. So that is the purpose of this real-time simulation, this real-time uh, simulators. First to do simulation and then to do some hardware in loop testing. This will allow us to design and see the operation of microgrid and also evaluate the protection of power devices before their actual installation. This was the case study which was used for simulation of AC microgrid. It's a simple, a very small AC microgrid connected to the main grid at 480 volts. And this is the point of common coupling. This is circuit breaker connecting with, which can, if there is a fault on the grid side, this AC microgrid can be disconnected from the main grid by this circuit breaker. And there are individual circuit breaker for each of these loads as well as the generation. In case of fault in any of these, the circuit breaker can be opened. Here we have one lithium-ion battery, one diesel generator, and one PV, and together these three are feeding a load of 0.5 megawatt, and PV is of 0.4 megawatts. Clearly, we can see the PV itself is not sufficient. The load is much, and the load is 100 kilowatts more than what PV can supply at its maximum. This is the maximum what PV can supply, but it will not always be at its maximum because it depends. It depends on the irradiance. This will be available only at 1000 watt per meter square. And this is not always there. This is only for a few 1 hour or so, few minutes maybe. But rest of the time, this insolation gradients will be even lesser, and the output of PV will be less than 0.4 megawatt or 400 kilowatt. In that case, we need the diesel generator, and or if it is grid connected, then we can get supply the load from the grid itself. And here we'll see, as we already seen in previous weeks, that we have different modes of operation for AC microgrid. One is grid connected mode, one is isolated mode, and there is also a transition mode from grid connected to isolated and isolated to grid connected modes. In grid connected mode, this AC microgrid is connected to the grid. In that case, the grid can supply the load. In this case, if the PV, whatever PV is generating, we will always want to get maximum out of PV, because grid is already there to feed the load. Whatever we can extract from solar, we would like to extract the maximum and try to charge the battery. So here PV will operate in its maximum power point. And because load is here more than PV alone cannot satisfy the load. We will always require this supply from grid or from the battery or diesel generator. So here PV generator can charge the battery. Here the grid supplies the load when there is no PV. Otherwise, when PV is there and storage both are able to meet, then grid is not required. We can directly supply the load by using PV and battery itself. And here PV operate at its maximum power point, because even if there is excess from here, let's say battery plus diesel generator plus PV, this is more than 0.5 megawatt. Then the excess generation from PV can be sent to the grid. PV operates at the maximum power point. And the storage will charge or discharge based upon the reference signal. It will be based upon its SOC. And then DG may help in voltage regulation by excitation control. The diesel generator can help in voltage regulation. Frequency control is achieved by power balance using the grid supply. So here, because grid is available, so frequency regulation part is not done by diesel generator. Only voltage regulation is diesel generator can help in voltage regulation here. If the voltage here goes down, then diesel generator can provide reactive power to improve the voltage level. Then in the isolated mode, PV may or may not operate at MPPT. In isolated mode, grid is not available. Grid is not available. Okay. Let's say so load is here 0.5, and because it's isolated mode, we need, and this is AC microgrid, we need to regulate both voltage and frequency. In this case, DG will be there. It will have to operate, and it will regulate both frequency and voltage. Now, let's say battery is there, battery is already charged, and diesel generator is also running, and both these are generating together, let's say 0.4 megawatt, and load is 0.5. PV need to provide only 0.1 megawatt. That's and let's say it can generate 0.2 megawatt, but we require only 0.1 megawatt. So now the PV will not be operating at its maximum power point. It will operate in as per the SOC of the battery. The PV, if the battery is fully charged, already fully charged, then PV cannot operate at its maximum power point. Once the SOC reaches 0.9, the storage cannot be further charged, and PV will have to change its operation from maximum power point. It cannot operate at maximum power point. Here we see this, out of these three, battery, generator, and PV, only the storage is connected to the AC grid by a bidirectional converter. Bidirectional AC-DC converter. PV and DC generator are connected by only a unidirectional converter. Just a minute. I think I need to change this. I need to share it. I will stop share and share this PDF again. Sorry, I am sharing this PDF now. There is some problem. PPT, it hangs. Okay, I think it's visible, right? So we were here. I was saying that this battery is uh, having a bidirectional converter, while others are having only a, this is having a unidirectional converter. Here, no converter is required. So in isolated mode, PV may or may not operate in MPPT, and storage will charge or discharge based upon its SOC. And the DG will operate in isochronous mode. That means maintain a constant speed and provide the voltage and frequency control. Here, the PV and battery operate in decoupled PQ strategy. We have seen in previous weeks that ABC, we use this DQ, this frame of reference. We change the frame of reference. Here we have ABC frame of reference. We convert it into DQ frame of reference. ABC here are sinusoids. These are sinusoidal waveforms. It- It's a current. If we have three currents, IA, IB, and IC, then all the current waveforms are sinusoids, separated from each other by 120 degrees. But if we use sinusoids and we want to use the PI converter, the PI controller, then the control design is very complicated. Is it becomes a very higher order, third or fourth order controller, and design is also very complicated. And it is no more a PI controller, it becomes a PR controller in that case, proportional resonant converters, sorry, controllers, PR controller, if we use sinusoids. To make the life simple and use our already known, widely used PI controllers, we change the frame of reference from ABC to DQ. And this is a transformation from one frame of reference to another. And these DQ signals are constant signals. Or we would say not constant, I would say DC. These are DC signals. During transient, they might change, but in steady state, they will be constant values. So we get DC signals. From sinusoids, we get DC signal, and these PI controllers, they work with DC signals. And that's why we change the frame of reference to get DC signals on which we can use our existing control theory. Okay, so here we are talking about the decoupled PQ control strategy, one for D axis, one for Q axis. So using D we can control the active power, using D we can control the reactive power. Then you already seen that, yes, here another thing is this PV and battery sources are interfaced to AC grid using dynamic average model. We can create different models when we are doing simulations. We can create a detailed model, we can have an average model, and we can have a steady state model. So this dynamic average model is different from the detailed model. In detailed model, we'll be able to capture even the transients very accurately. So in detailed model will contain all these details of the switching transients of the switches. The switches will be modeled in great details in that case. In the converters which we are using here. In PV, we are using this buck converter, this boost converter, and in battery, we are using bidirectional buck boost converter. Their switches will be modeled in great detail in the detailed model, and we will be able to capture let's say the switching frequency is 10 kilohertz. We will be able to capture all the signals of frequency 0.1 milli. So 0.1 is saying frequency was 10 kilohertz, right? In 0.1 milliseconds. We can see transients of this order. We can track all the signals of this 10 kilohertz frequency. But in this dynamic average model, we will not be able to see these transients, but we'll be able to see the steady state behavior very accurately. So this here we can use large time step. The time step which is used for the model when we are solving any, let's say we are using Simulink and we want to solve the model, we need to specify the time step. And the time step which we specify depends upon what we want to see. Let us say in this, when we have power electronic devices, the frequency is, the highest frequency is equal to that switching frequency of the device generally. And let's say it is of the order of 10 kilohertz. This is the highest frequency. And because we have sinusoids, then we have fundamental frequency of 50 hertz. In steady state, we will be having this 50 hertz. In transients, we will be seeing this. Okay, even in normal operation, we can see the switching of these switches. Now we can see the frequency ranges from 50 hertz to 10 kilohertz. And we want to see, we are not, let's say we are not bothered about these switching transients. We are only interested in this fundamental frequency. We are not even bothered about harmonics. We are not doing any harmonic analysis. We just only are worried about this fundamental frequency. Then this is equivalent to 20 milliseconds, right? Then in that case, the time step has to be at least this much. To observe this frequency, we need to have a time step of 20 milliseconds. If the time step is more than that, we will not even be able to capture this 50 hertz. The time step which we set for the solving the model, it depends upon which frequency we want to see. Let's say we want to see both these, then the time step will be governed by the highest frequency. Because we want to capture the highest frequency, then the time step has to reduce. It will be 1 by 10 kilohertz. So it will be 0.1 milliseconds. Now we need to reduce the time step. And the higher the frequency component we want to observe, we need to reduce the time steps. We need to reduce the time step. Therefore, and reducing the time step increases the computation requirement because it requires solving the model for very small, continuously for at that time step. For each 1 millisecond, we want to solve the model compared to the 20 millisecond. It is 20 difference of 200 times. So that's why computation will increase. And to reduce this, and if we are not even concerned about the transients, we can go for the average model. And here we will be able to see the steady state behavior, and we can also work with larger time step, which will solve the model quickly. That's why we use the dynamic average model. But if we specifically want to see the switching transients, then we need to go for the detailed model. Is it clear? Dynamic average model, they do not represent high switching frequency dynamics, reducing the computational requirement and allows higher simulation time step. The same thing which I was telling. Then diesel generator, we already seen that it has two, because in isolated mode it wants to, we need to regulate both voltage and frequency, and for that diesel generator is having speed governor and the excitation system. Speed governor for regulating the voltage, it will, no sorry, for regulating the frequency. So it will help to regulate the speed, which in turn regulates the speed is equivalent to frequency. And by changing the mechanical input, we can change the frequency of the voltage generated by the diesel generator. Similarly, it has an excitation control by which we can control the voltage at its terminal. It helps to regulate the terminal voltage by varying the field current. In overexcited mode, it will inject reactive power. In underexcited, it will absorb. And in normal excitation, it will be operating at unity power factor. So this is very important. You need to you can remember these things. And yeah, we've already seen that there are two modes. This is the overall summary of how the AC microgrid will operate in the two modes. In grid connected mode, we have two options. Now, uh, two types of operation during different types of requirements, which are off peak hours when the demand is less, peak hours when demand is high. In off peak hours, the storage will charge and PV will operate at its maximum power point so that it charges the energy storage. And the diesel generator, because it is grid connected mode, so diesel generator will only be helping in the voltage regulation, not frequency regulation. In peak hour, energy storage will discharge, here demand increases. And in off peak hour, generally, if it is discharging, PV will be operating at its reduced PV at MPPT. When off peak hour, the irradiance is less. The PV output will be less, but still it will be operating at its maximum power point. And then diesel generator is still operating in voltage regulation mode. Now in isolated mode, the diesel generator has to regulate both voltage and frequency. It will be regulating both voltage and frequency. Here the energy storage will charge and PV it at MPPT at off peak hours. And similarly for peak hours also. Difference only is of here diesel generator, which is of regulating both voltage and frequency in the isolated mode. Now this is the example of a simulation of DC microgrid. Previous one was AC. Now we are moving on to the DC microgrid. Here it's a standalone DC microgrid. We can say it is operating in the isolated mode. It's not connected to the main grid. It's a one village is there and it is completely being supplied by the distributed generators, diesel generator, no, all the distributed generator as well as storage. Here we have PV panels, we have wind turbine, we have a diesel generator and a hybrid storage composed of battery and supercapacitor. Supercapacitor for high frequency uh, transitions, for high power requirement, high power, because the power density of supercapacity is largest compared to the storage, the lithium ion. And the lithium ion energy capacity is more as compared to the supercapacitor. These two are complementary and they help us to, because if we use supercapacitor, then the frequent charging, this frequent charging discharging operation can be avoided of lithium ion, which degrades its performance or life cycle. That's why we use supercapacitor here for providing this fast response. And for slower discharge, battery can be used. So the PV here is connected to the DC bus. This is a DC bus, common DC bus. And PV is connected to the DC bus via a boost converter. Let's say because this voltage here for PV panel is less and DC bus is at a higher voltage level, we need a boost converter. Let's say unidirectional boost converter. Diesel generator It will generate in AC. We need to convert it into DC. It's a controlled rectifier, AC to DC. Because here we do not want simply to convert AC into DC. Let's say it is operating at 230 volts. It is generating 230 volts. And if we convert it into DC, then it will simply give us an equivalent voltage. Two Vm by pi. It will be 2 root 2 into 230 by pi. This will be the output here. But here the DC bus voltage might be different. We don't want this. We want to reduce this or make it equal to DC bus. So reduce only. That's why we want to have a control over this. We need to multiply here by. If we have a control, this will be for a diode rectifier. If we have a controlled rectifier, then it will be 2 Vm by pi cos alpha, where cos alpha is the firing angle. We can change the alpha to match the output with this DC bus voltage. Similarly, here we have this wind. It is converted into DC, and then here we have a controlled rectifier. And here we have a chopper. And we have three loads, out of which one is a critical load, which has to be met at any cost, and other two are non-critical loads. And this battery and supercapacitor are connected to this DC bus via a bidirectional buck boost converter. Here, this philosophy is also similar to what we have seen in AC microgrid. We'll just once go through it. It starts here. First thing it checks is the controller of this microgrid will check is how much is the generation and how much is the load. Is the generation more than the load or less than the load? That is the first question. If the generation PG is more than the load, yes. Then the next question is, what is the status of the battery? Is the SOC more than 90%? If it is more than 90%, then the PV and wind, they cannot operate in MPPT mode. They will have to go to the bus regulation mode, and battery cannot be charged because it is already charged up to 90%. If the SOC is less than 90%, then battery can be charged by operating PV and wind in the maximum power point mode. This is when the generation is more than the load. Now, if the generation is not more than the load, generation is less than the load, then we check what is the status of the battery. If the SOC is SOC less than 40%, no, then battery will discharge and PV and wind operate in maximum power point. So whatever is there, we want to extract maximum from PV and wind, and remaining battery will supply. Now go to the, if SOC is less than 40%, then we need to check whether diesel generator is available. If diesel generator is not available, then we will go to here and we check the SOC. If SOC is less than 40%, is not less than 40%, battery will discharge and meet all the loads, critical as well as non-critical. If SOC is less than 30%, if SOC is between 40 and 30%, then one non-critical load will not be supplied. And if SOC is less than 30%, then only the critical load is met. Other two non-critical loads are not supplied. If DG is not available, but if diesel generator is available, then the difference between the generation and load, and if this difference between load and generation, let's say this is some P, and if this P is less than PDG, means diesel generator is generated more than what is required, excess generation, then it will charge the battery. But if it is generating less than what is required, then we need to go to the battery. We need to discharge the battery. And if SOC is less than 30%, and SOC if less than 20%, then only one critical load is met. If it is between 20 and 30%, then one non-critical load is curtailed. If it is more than 30% and less than 40%, then the all the loads are supplied. So this is the way we cover all the scenarios, different scenarios which can happen, and on the scenarios, our aim is to supply the critical load. And for that, this strategy is designed. This was the simulation for the DC microgrid. And next is the interconnection of two local DC grids. This is one DC grid which we have already seen here, this type of a DC grid. And this is another DC microgrid. And both are interconnected by a dual active bridge. It's a bidirectional, high power feeding capability and with large conversion ratios. And because we have a transformer here, it provides galvanic isolation also. Why do we connect these two DC microgrid with each other? Let's say these are two different localities, two different communities. One is being supplied with the microgrid 1 and second one is being supplied with the microgrid 2. And let's say there is excess power generation in microgrid 1 and a deficit in microgrid 2. Instead of using the diesel generator available here in microgrid 2, if these two grids are connected, then the excess power from microgrid 1 can flow to the microgrid 2. And this will make it more eco-friendly because we want to use the diesel generator as less as possible. So this will, and yeah, this can also, interconnection can also help us connect two grids at two different voltage levels. One might be at 340 volts, other might be at 48 volts. Two different voltage levels can be connected together, just as we connect transmission lines, and on the both side of transmission line we can have different voltage levels because in between we have the transformer. Here also we are having this transformer, and because of this transformer we are getting this large conversion ratio. In the classic or the conventional choppers or the boost converter that we have, boost converter, which is first order convert. It's a, we have an L and C, so second order. Okay, here we have only one diode, one switch, and one inductor in boost converter. Here we can go only up to a conversion ratio of 4. Let's say the input voltage is 10 volts, maximum we can make it boost up to 40 volts. But more than that we cannot get here. But if you see the conversion ratio here, what is the conversion ratio? Can you tell? How much converts? What's the conversion ratio we require here? Let's say this is 350 approximately, and 50, then it is approximately 7. Conversion ratio of 7. And a boost converter cannot provide us that type of conversion ratio. We need to go for other types of these converters, push-pull converter, choke converter, and all that. And dual back-to bridge is another one. So this is bidirectional. We want bidirectional, and we also require isolation, because if there is a fault here, this side will not be affected by that because of this galvanic isolation. So these are the advantages. And so yes, this is done that we can connect the two grids at two different voltage level. Then we can have local energy security and reduction in cost if we are not using diesel generator. High reliability if there is less generation here, we can import generation from the other grid. Uh, Still we can meet the load. That's why reliability is increased here. And the supply quality can also improve here in this case. The next one was this AC/DC hybrid microgrid. And here the main thing which was discussed was the current coordinated voltage control scheme. How to maintain the voltage profile in distribution system as we move along the feeder. Because in distribution system, especially the rural feeders, they are very long. And the traditional, if we see the traditional distribution feeders, then there was no distributed generation. There was only one substation from which was connected to the grid, and from here we have feeders. We have different feeders. We have laterals, so many laterals, and feeders are there many. So different feeders are there. Long feeders are there. So suppose there is this voltage at substation is 1 per unit. But as we move along the feeder, especially to the far end of the feeder, then the voltage reduces significantly. And for that, we have on-load tap changing transformer here at the substation. Or we can have capacitor banks in between to boost the voltage. Different reactive power devices are required. So in traditional distribution system, we had whenever there was a voltage, means the load is increased, or at regular intervals we have these transformers. In US, they have OLTC, on-load tap changing transformer in the substation. And now in active distribution system, there are other devices also. We have capacitors, then we have D-STATCOM, dynamic voltage regulators, DVR is also there. Then we can have a microgrid can also help in voltage regulation. We have already seen that in the previous part. It can also help in voltage regulation. So these different voltage support devices can help us to maintain the voltage profile here. And they need to coordinate with each other, right? They need to work in a coordinated fashion to achieve the voltage profile, to maintain the voltage profile. So that is the coordinated voltage control scheme. And it can be centralized or decentralized. Centralized will require communication between all these things and with the controller. Decentralized does not require any kind of communication. So here aim is to optimally utilize different compensating. So these are different reactive power compensating devices. And the objective is to optimally utilize these and to increase the overall reactive power reserve. So in case there is some fault, the post-fault recovery time will reduce if the voltage, if the reactive power reserve is high, then the recovery, the post-fault recovery will be very fast, very quick. If there is a reserve is more. So that's why it reduces the post-fault voltage recovery time. If we are able to, and out of these, some are small, slow acting devices, and some are very fast. Power electronic based devices are all very fast. This OLTC and capacitor bank switched capacitors, these are slow acting devices. While the other, the D-STATCOM is a very quick, very fast devices. So these fast device, this will act very fast, very quickly, and the slow will not get even time to act. By the time the fast is able to do, slow will, so slow devices are not utilized optimally in that case. So here we have three states. State 1, which is a steady state. Here the requirement of reactive power is less than 40% of the rated reactive power which these devices can provide. More than that is not required in steady state. With 40% also we can work. The transient state requires 100% of reactive power. This is when there is some fault. Let's say there is a triple LG fault. In this case, the voltage will reduce less than 0.9. It will go suddenly, the voltage will drop when there is a fault. And in this dynamic state, the Q requirement is hard limited to 40%. And this happens when there is a, one example is sudden load switching. So here less than 40%, here 40%, and here up to 100%. So from this state to this state, we can move when the reactive power requirement reduces less than 40%. And the voltage is still more than 90% or 0.9 per unit. From here to here we go when the requirement of Q increases beyond 40% and voltage is still above 9 per unit, 0.9 per unit. Okay, similarly we can move from one state to another. And this is called state diagram. And you would have seen such diagrams in computer system also. You can, the state machine, state transition diagram, it's also called state transition diagram. A Moore machine or Mealy machine you would have studied somewhere in computer science if you have come across these words. So here we saw two types of different schemes which are used for this coordinated voltage control. The existing scheme and the one which is proposed in the lecture, they have some difference, and the existing is further able to utilize them more efficiently, all the devices. The existing schemes, they give importance only to the speed of operation of the device, and they do not check for availability of device. Only bothered about the speed, and all of the device act together. There is no distinction between slow and fast acting devices. As a result of this, there is poor utilization of these slow devices because they act very slowly and the fast are able to meet the requirement. The new scheme, they have more effective utilization of all the devices. They improve the voltage profile, improve the fault ride through, and also improve the transient condition. That means the post-fault voltage recovery time that is reduced in this new scheme. Very quickly it is able to achieve that normal state. So for doing this, um, the control strategy is divided into three stages, where the first stage is to identify the operating condition of the grid. And then based upon that, the operating condition is these three conditions based upon the voltage and the reactive power requirement. The state is determined. The operating condition of the grid is determined. So these arrows, they can help us determine the operating condition of the grid. Once this is determined, whether it is steady state or dynamic or transient, once we know this, we distinguish the devices. The first step is to distinguish the operating condition. Second is to distinguish between the devices, which one is slow, which one is fast. So slow one will act as the master and the fast one will act as the slave. The slave will follow the master. So check for the availability of device. Now identify the device. Now check the availability of the device and then assign them master slave rule. The slow will become master and fast will become slave. And then after that, introduce a time delay in the operation. Because we have seen here that here slow device was not utilized properly. So a time delay is introduced for the fast device so that slow can act first and then fast will act. Now slow will also be utilized properly. So time delay is introduced for the fast acting device. In this way, all the devices which are available, they are able to they are properly utilized, effectively utilized. Okay. And because of that, and because of this, the reactive power availability increases, the reserve will increase. And that's why the post-fault voltage recovery time also reduces. Okay, that was the which one? The demonstration for that AC-DC hybrid microgrid. Now next one is the challenge is this demonstration of the parallel operation of inverters in AC microgrid. In any plant, if you see in a DC in a solar farm or a wind plant, there is not there is not a single inverter. We call them string inverter or string combiner boxes. So there will be different. Means we have seen this in previous weeks when I think week 2 where we were discussing different distributed generator. I had distributed generations. I had shown one uh, single line diagram for solar plant, how they are combined. The different strings of solar panels or solar arrays are combined. One string has many number of arrays, and there are several such string in parallel, and they have one combiner box, which is called a string combiner box. And we have an inverter here and transformer here. Similarly, we have other strings also. So these are in parallel. Let's say there is one 5 MVA plant. This is 1 MVA transformer here, 1 MVA inverter. Similar, so we'll be having 5 such 1 MVA inverters. So these 5 inverters will be operating in parallel. These are all similar inverters, similar rating. So we are talking about such a configuration here. Each plant will be having all such plants will also be operating in parallel finally. In parallel operation, we have this phenomena. We have when these more more than one inverters are there, so two or more inverters are in parallel, then there are two types of current which are there. One inverter is this, second inverter is this, and both are con providing feeding to the grid. In this case, we have two types of current here. So one is the interactive current, and another is the common current. The common current is the one which is actually delivering power to the into the grid. And this interactive current is one which is equal in magnitude but opposite in phase. If everything is equal, the reference currents are equal, then they will cancel out each other and it will be the net effect will be zero. But if there are some differences, the reference current are different, then because their magnitude will be different, but they will be out of phase, so overall magnitude will be net result will be reduced. So that will create here losses here in between in inverters. We also call them the circulating currents are also in we have seen these circulating currents in parallel operation of generators. It's same thing is happening here. We have interactive currents and these flow between the inverters and they have main thing is they are out of phase and they have these are high frequency oscillation and their frequency of oscillation is equal to the resonant frequency of the LCL filter. So each of these inverter is connected to the grid via a LCL filter. If we use L filter, then we do not see this phenomenon of interactive currents. It's not there because that is in L filter is only a first order filter. In that case, we do not see because directly the whatever current is here, it will that current directly goes. But here, because of L and C component, we have resonance here, and because of resonance, these current are there. And then this common current we already discussed, these are the current which actually flow into the grid and they are responsible for delivering power into the grid. So this is the diagram which you've seen. So this is the reference current 1 for the first converter. This is the reference current 2 for the second converter. And the final, the interactive current which we find. So interactive current and then right. This is let's say this is common current and this is interactive current I in. So this is proportional to the I ref1 plus I ref2 and this is proportional to the difference. If these two are same, then it will be 0. But if they are different, then non-zero. And common current is sum of proportion to the sum of these two. Here we have two such inverter. If we have three, then we can have one more, and in that case, this will be I23. This will become a 3 by 3 matrix. We will be having one more row and column, and this will become V03, the pole voltage. These are the pole voltage V01, V02. And this is the LCL filter, and these finally find that these are the two resonant frequency for the two converters, for the two inverters. There are two resonant frequency for two inverters. One is for the common current. Sorry, it's not working. The difference between these two frequencies is there is only a difference of this LG. grid impedance. In omega r, there is no grid impedance. In omega r1, there is a grid impedance. Similarly, if you see GP and GC, there is a difference only of the grid impedance. So GC is for the if you will find the in this expression for common current, it will be proportional to GC. GC and that interactive current will be proportional to the GP. Common current, we have this impedance term, grid impedance LG. Okay. Yes. And now it's okay. Okay, so the last topic which was discussed in this week was the harmonic effects and mitigation strategies. Power quality, these are all power quality issues. Harmonics is one kind of power quality issue. The power quality deteriorates when there is a deviation. The normal voltage and current waveforms are sinusoid. Right? This is voltage and so this is current. Normal current and voltages are of 50 hertz and a constant frequency and some constant magnitude, let's say 230 volts RMS. Okay, this is normal sinusoids. Voltage and current waveforms will have constant voltage and frequency. But once they deviate from these normal sinusoids, any kind of deviation that will fall under the power quality issues. That means any kind of deviation from these ideal sinusoids will result in deterioration of the power quality. And that can be because of different reasons. And these are these different reasons. And they are categorized into two parts. One is the voltage related issues. Second one is the current related issues. In voltage related issues, we can have voltage sag. That means the voltage is reducing. We will see in the next slide. Then voltage swell, voltage interruption, and current related harmonics is a current related issue. Another one is notch, then transients and unbalanced load. Theoretically, we can measure harmonic by THD, total harmonic distortion. And practically, we have these power quality analyzers, which provide us the harmonic spectrum. What all harmonic components are present. The sorry. So these harmonics have adverse effects. And they have they have adverse interaction with other power system equipments. They result in additional heating and losses in motors and transformers. And then they interfere with the telecommunication lines. And they also create errors in power metering and control circuit. Even when we do protection, then the second harmonic restraint relays are there. So first of all, the signal which is there, voltage and current, from that the second harmonic is first of all removed, and then the protection decisions are made. See, otherwise, if we consider that if we do not what to say verify or uh, condition the signal, do not improve the signal, then the decision, the power, the decision, the power, the protection philosophy or algorithm will make will not be correct. That's why first of all the harmonics are removed and we only consider the fundamental frequency. We also seen that least square we when we in fourth or fifth week we saw the phasor estimation techniques, right? In that we only need the fundamental frequency and we have seen this least square least square method where we had seen that we can have all the different frequency components we can capture and even the DC signal also, decaying DC component. We were concerned with the fundamental and we need to take that only. That's why this measuring harmonics is important and to reduce their influence in the signals, voltage and current is also very important because if the signal, this voltage and current signal, they deteriorate, then they affect our equipments. That's why we have different types of these filters to improve, to remove these harmonics. We have different high pass filters to remove these higher order harmonics, or low pass filters for lower. Then we'll be having higher order harmonics, so high pass filters. When we use the different types of power electronic, these uh, converters in rectifiers, as we increase the number of stages, the harmonic level also reduces. In 3 pulse or 6 pulse converter, only 6 harmonics are there. This fifth harmonics are not there. 6 and plus minus 1 are there. The fifth is there, then 11th is there. So we have eliminated third, seventh, ninth. The fifth, 11th, and these are then eliminated using filters. So there are different ways by which we try to, and by these sinusoidal pulse width modulation also, we can, by proper modulation, pulse width modulation also we can do that. We can eliminate certain harmonics. So we try to eliminate the lower order harmonics so that higher order harmonics we can easily remove by using a lower size filter. For lower order harmonics, the filter size will be very high, very large. Here we see different types of power quality issues. This is the ideal voltage sinusoid. Now this is the voltage sag where the voltage magnitude reduces for a few time blocks. Similarly, if the voltage magnitude increases temporarily for few cycles, then it's a voltage swell. But if there is a temporary, there is voltage is becoming zero for few cycles, then it is interruption. Here it is reduction in voltage magnitude, increase in voltage magnitude, but this is zero voltage for few cycles. That is interruption. So this is the difference between sag and interruption. Here we can see the voltage profile is a sinusoid is maintained here, but there is a reduction in the RMS voltage. There is an increase in RMS voltage, but here voltage is no more. There is a zero voltage, total interruption. Here, this is the ideal current sinusoid. This, due to non-linear loads, the current changes. Waveform is changing because of non-linearity. And here these are the notches, high frequency component in the current. These are these are very high frequency component notches. These temporary flickers or notches. Then third one is the unbalance in the current. You can see unbalancing is different phase. This phase current is very high as compared to the other two. So there is an unbalance in the current because of unbalanced loading. The three phases might be having different loads, and because of that, there is imbalance in the current. And then we have this harmonics here. All the phases magnitude is same, but the fundamental is superimposed with other frequency components also. That's why it's a, there are harmonics in this current. And last one is the one phase jump. In one phase, there is no current here, similar to this. Here, no voltage for all the three phases. But here, one phase is out of service. Two phases are still there, but one phase is not available. Okay, let us move ahead now. Now, this is what we say mitigation. We have discussed the power quality issues. We have discussed the power quality issues, and now we are into the mitigation strategies. Once we have these different types of issues, how to mitigate them. And we can do that by using filters. One option is to use the passive filters. Another option is to use the active filters. Passive filters are widely used in HVAC, high voltage AC, because of their simple design, because of their robust nature, and because of their cheaper, because they are cheap. They are cheaper. They are simple and they have robust design. But the problem with them is that once we tune them and the system changes, then they, their value will not be appropriate for that system, for the changed system. They might become oversized, and that will further deform the uh, distort the waveforms. That's a passive filter are only meant for a particular system, or you can say the range of system, a range of uh, values, because in passive filters we can have two. One is fixed, one is switched. So fixed one is only for a particular value, and switched one will be having a providing a range of fixed capacitances or fixed inductor. So that can work for a range of voltage values, but for beyond that will not be able to work. And that's why if there is a overcompensation, then that will also result in a problem. Let's say in light loading condition, in transmission lines in light loading condition, there is Ferranti effect. And if you already have capacitances also, then it will further boost the voltage. It will enhance, it will further increase the Ferranti effect, increase the voltage rise on the receiving end. Receiving end voltage will further increase because of the presence of these capacitances. That's why active filters are used, although they are costly, but with the increase in the technology of these power electronic devices, these active filters came into being. And we have the shunt filters here as series filters and combination of shunt and series. So shunt filters are D Stratcom. In passive also we can have shunt series and hybrid of them. So here shunt is D Stratcom, active is DVR, and then combination of shunt and series is UPQC, Unified Power Controller. And this is one experimental hardware setup for this. Here we are using back-to-back converters. One is acting as a series active filter and one is acting as a shunt active filter. The load side is acting as a shunt, and this utility grid side is acting as a series shunt filter. Series active filter, shunt active filter. Okay, let us move to the questions now. What's the purpose of microgrid modeling and simulation? We have already discussed this. Now we have to select what. Let me just sip water. Sorry. The purpose of microgrid modeling and simulation is or are first, conducting rigorous analysis, identify key challenges. Yeah, we already seen, yes, we require to do rigorous analysis before we can uh, implement the same thing in reality. And we also, while doing analysis, we also find out what are the key challenges that we will be facing while actually implementing that thing. So that is also very important. Then feasible solutions before physical implementation. Yes, once we have challenges, once we do analysis, we'll also get what are the solutions for these challenges. All of these are purpose of microgrid modeling and simulation. All of these are correct answers. Next, moving on to next one. Identify the incorrect statements with regards to inverter control of PV and battery in microgrid. The first one, PV and storage controls are based on decoupled PQ control strategies. Yes, this is correct. We have seen that ABC, we convert that space phasor domain, we go to the uh, DQ frame of reference, where here we have sinusoids. From sinusoids or space phasor, we go to DC signals. And then we can use the our PI controllers. We can get a simple control design here. Simpler control design in this case. Yeah, so we have only two here. Here we need three convert. First of all, here we need three PR controllers, for one for each phase, and here we need only two PI controllers. Then PV and battery sources are interfaced to the AC grid using dynamic average model of their DC AC voltage source converters. Yes. Why do we need that? Also, we have seen why average model will work, because if we want to see only if we are only concerned about the steady state behavior, we are only concerned about the we do not want to track the high frequency. Do not want to track the high frequency switching transients, then we can work with the dynamic average model. The dynamic average model represents high frequency switching dynamics. No, although the word dynamic is here, but it is average of the dynamics, so it will not it will not represent the high frequency dynamics. It will only provide us the average of those dynamics. And dynamic average model allows higher simulation time step. Yes, correct. Because here we are only worried about the steady state. So here the frequency under study is lower. So we can go for higher time steps, higher simulation time steps because of that. The higher the frequency we want to monitor or analyze, the lesser the time step we need to have. And because of higher simulation time step, we can save the computation requirement. We can save on the computation, this will reduce the computation requirement, computation time. Okay. So what was the incorrect? So C, this one statement is incorrect here. The function of diesel generator in AC microgrid is or are frequency regulation by changing the mechanical input of the rotor. Yes, correct. And this will be in the isolated mode. Yeah, islanded mode. Because in grid connected mode, it will be doing only the voltage regulation. Terminal voltage regulation by varying the field current through excitation. Yes, this is in the grid connected mode. And then normally excited operated, no, this is not correct. It will operate at UPF. Function A and B is correct in this case. Yes, very good. Which statement is or are correct with regards to inter-DC power flow? What have inter-DC power flow? Effective control and coordination is achieved without communication. High control complexity and centralized control. Isolation is not provided. Low reliability and embraces extreme scenario of individual grid. It provides effective control and coordination without communication. Which of these are voltage regulating or reactive power compensating devices? Which one is the correct voltage regulating? Which of these are voltage regulating devices? OLTC, D-STATCOM, DC microgrid, all of the above. Yes, this is correct. Moving on to the next question, which of the following statements is or are true regarding interactive currents? What do you think? Interactive current, it's a current component with high frequency oscillation. Yes, this is correct because its frequency is equals to the resonant frequency of uh, LCL filter. It flows between the two inverters. This is also correct. And frequency is twice the frequency of LCL filter. And this is not correct. The first two are correct here. It's a current component with high frequency oscillation. And it flows between the two inverters while the common current flows into the grid responsible for delivering power into the grid. Select the correct option for parallel operation of two inverters in microgrid. Common current is responsible for feeding power into the grid. Yes, it is correct. Common current is proportional to the difference between reference current. This is not correct. This interactive current is proportional. Interactive current is proportional to I ref1 minus I ref2. while the common current is proportional to the IREF 1 plus IREF 2. This is okay. Interactive current of an inverter is sum of two components. Difference. Problem of is sum of two components. This is correct. It is sum. Problem of interactive current and common resonance does not occur in L filtered. Yes, this is correct because it is a first order. This phenomena is not there in first order filters. Yeah, so this is correct, and this is correct. Which of the following are current related power quality issues? One is harmonic. Yes, we already seen. Let us go through that again. Yeah, this in power quality issues we have two category: voltage related, current related. In voltage related, we have voltage sag, voltage swell, and voltage interruption. And in current related, we have harmonics, notches, transients, and unbalanced load. Okay. Yeah. So current related are harmonic, notches, and unbalanced loads. Voltage, sag, swell, and interruption are not. These are voltage related. Disadvantages of passive filters are is or are. Yes, large size filter is required and causes overcompensation, and it changes with the system requirement. Does not track system requirements. So it is not adaptive. This is not adaptive. Change in system detunes the filter and causes increased distortion. Correct. Adaptable to varying system condition as size and frequency can be quickly altered. No, these are not adaptable to varying system condition, and that's why we need the active filters. And they are fixed or mostly either their value is completely fixed or they are switched, but still but not adaptable. Okay, I think this is the last question. Yeah, this is the last question. An OLTC is connected between nodes 1 and 2, regulating the voltage at node 2 with respect to node 1. Node 1 voltage is 1.01 per unit, and the tap is 6 plus 6. Compute the voltage at node 2. We need to find V2. So this is a simple formula here. V1 into 1 plus 1.00625 into tap position. Here we know this is 6 plus 6 and V1 is 1.01. This is 1 plus 0.00625 into 6. Okay. This will be equals to how much? This will be 1.047875 per unit. But this will not generally be the case, right? Uh, Generally, V1 will be higher than V2 for the power to flow like this. When can this happen? V2 is more than V1. Generally, for power to flow from V1 to V2, V1 has to be more than V2, right? For that, the tap has to be negative, at negative position. But if V2 is more than V1, is it possible? Yes, it can be possible. It is possible if let's say there is a solar PV at V2 and during daytime, and it's operating at PV at MPPT, high solar irradiance. In that case, what is happening? The voltage will increase. We have high voltages in that case. So we want to take care of all this, and so this is the last question. This was last question. If, uh, if you have any doubt, you can ask. Otherwise, we will stop the session here and we will meet next week, Monday, same time 6 to 8. Now we are remaining with only 2 weeks. This was week 10, then we have week 11 and week 12 only remaining with us. And if you want an extra session, we can have one extra session which will be what we say, a demo, not demo, sorry, summary of all the sessions where we can take questions from all the weeks. You can get all your doubts from all the weeks. You can come up with your doubts and clear them here in the next session. In not next session, in that session, which is the last session, which we want as a summary session after the week 11 and week 12 session. We will be having that on which date? That has to be on or before 16th. So 11th session we'll be having on 7th, 12th on 14th, and then 16th itself we will be having that extra session if it is there. 7th and 14th. Okay. So that's all for today. We will meet next week. Thank you very much for joining.